Thank you.
Thank you very much for the introduction, Karen. So my name is Herve, and today we'll be talking about GEOSX, toward net zero, tools to simulate gigaton scale CO2 storage. I have the pleasure of presenting today, but know that this is a body of work that was done by many people. About 30 people have coded in this platform. Many more have done research that fed into the code. And this is a joint project between Stanford, Lawrence Livermore National Lab, and us at Total. My email address is here on this front slide. You can always reach out to me, but as soon as everything gets back in order, you should be able to see me on campus at the Greener Science Building department, the Greener Science Building in the Petroleum Engineering, Energy Resources Engineering department. I'm usually there on the 3rd floor. Here is the summary of the talk today, and this is, I guess, how it's been described to you. And this is me with a suit on. You're probably not going to recognize me if you see me walking on campus because I seldom wear a suit. But anyway, this is me. So geological sequestration of CO2 is one of the solutions to reduce atmospheric CO2 concentrations. Now, modeling and simulating that is quite difficult. It requires advanced multiphysics, high-performance computing, and really, we can't do this alone. So Lawrence Livermore National Lab, Stanford University, and Total have worked together on creating such a tool. This partnership started in 2018, but it's not just the starting date of such an effort. These efforts have started long ago. This is just one collaboration we have. And today we are going to present to you this particular effort and give you opportunities to contribute if you wish to this. So let's start. Maybe let's just zoom out and take a look about and think about what energy is going to look like in 2050. So this is your average person today, consuming about 100 gigajoules a year. And so I've looked at my numbers just to make sure they were correct. If you're living in Spain or if you're living in China, this is about what you're consuming every year. It can be a little more if you're in the US, a little less if you're in Bangladesh, but let's assume that this is a good average number for how much energy you need every year. In 2050, we'll have to multiply this number by about 10 billion people. So the estimations vary a bit, but this is a good approximation for how many people will be on the globe at that time. So we're looking at 1 zettajoule of energy to be supplied to the world. That's 10 to the power 21 joules or something of that order. And just just to put things in perspective, this is about twice the energy system that we have today. 2018, we've estimated about 600 hexajoules. So we're going to have to multiply this number by 2 if we want to continue to have 100 gigajoule per human by 2050. So this is a relatively important challenge, but it's even more difficult to achieve this if we want to do this while reducing carbon emissions. So here I've put quotes on this sentence because when the person that says it's our job to meet growing energy needs while reducing carbon emissions is the CEO of Total. I've taken this quote from one of his reports, and it really shows that there is a big challenge there. I mean, this year you've all been dealing with 3 challenges: health challenges, economic challenges, and we're throwing on the climate challenge on top of this. So we want to be able to produce energy while reducing carbon emissions. The numbers here, the sources, the World Bank has great data sources, and the Global Energy Review for 2021 from the IEA is where I got those numbers from. This is a subject that you will read and hear about everywhere. This is from today, from the Financial Times. They have a special report on the future of energy. And here, if you see the subtitle, "The Rise of Renewable Energy is Prompting Change in Power Networks. How are governments and the energy industry responding? Can demands for more power coexist with pressure to cut carbon emissions?" This is the question that I want to ask today. what does the future hold for energy? Again, the IEA, same story here, energy on one side, CO2 emissions on the other. And global CO2 emissions have rebounded in 2021 already. So in 2020, we had a bit of a reprieve with a reduction of the emissions of CO2. 2 gigatons of CO2 were emitted less than normally. And now we're back into pre-pandemic levels already. So this is an important challenge. Now, if we reduce this and focus more on the global warming and anthropogenic greenhouse gas emissions, this is what the situation looked like all the way up to 2018. So I don't have pandemic numbers here, but you can assume a plateau after 2018 and perhaps a rebound in 2021. The greenhouse gas emissions can be broken down into 6 principal components. You have methane, 24%. You have CO2 from land use change, and forestry. If we want to take a shortcut, we can say this is just forest fires and removing forest, burning forest in favor of more profitable usage of land. 3% is from cement and flaring. Cement is perhaps one of the industry that alone has the largest CO2 emission footprint. And the rest is from gas, oil, and coal. And 70% of those emissions are coming from, or of those greenhouse gases are CO2. So reducing CO2 is really an important challenge. We're talking about 55 gigaton CO2 equivalent in 2018. There's about 40 gigaton of CO2 emissions every year. Now, if we look at what the energy demand looks like, we see that we have a relatively stable outlook, even in the rupture scenario. So here I see the IEA SDS scenario, which is the 2-degree Paris scenario. Then the TOE rupture scenario, this is Total's scenario for a technological breakthrough. So everybody drives electric cars. We are reducing our dependency on fossil fuels significantly. Still, we can see that gas, oil, and coal are going to still be there. So we can expect the emissions of CO2 to be relatively stable or to increase slightly by 2040, 2050. So this, some of you may have seen this picture many times. It's been used and used over and over again, but I think this gives you an idea for the rich landscape of possible research avenues and solutions for CO2, for atmospheric CO2 reduction. So if we just walk through this graph together slowly, on the left-hand side here, you see CO2 reuse and negative emissions. So we're talking here about everything that is emitted, the 40 gigaton of CO2 per year that are emitted. We're going to have to do something about it to reduce that. So we can reduce those emissions, or we can sequester and create what we call negative emissions. 2 sources, concentrated or air captures, many capture and conversion processes, all of those that you see here, advanced combustion, solvent, sorbent, cryogenic, those are all excellent research topics, and everybody that is remotely concerned with climate change should take a look at what those solutions can be. Then we have the CO2 capture product, so either supercritical or gas phase CO2, solid hydrocarbons, inorganic carbon. And then we have pathways and end states. So that means we have possible ways we can either use or dispose of CO2. And here you can see that just at the edge between CO2 reuse and sequestration is geological formations. And this is what we're going to be talking about today. But I just want to give you the impression here, or give you a sense that this is just a very small part of what can be done to reduce atmospheric CO2 concentrations. It's just one among many. It's a very important one, though. Here is what the IEA is estimating is needed by 2050. And this is the levels we are at today. So we're going to need about 80 times more volumes of CO2 injected per year if we want to get to the IEA levels. And in the title of my presentation, when we're talking about gigaton scale CO2, this is really what we're targeting. So in 2050, we're going to have to inject several billion tons of CO2 per year if we want to stay in a 2 degree C climate agreement. So now, of course, who is going to do that? Well, this is where oil companies, and this is where many others are going to take part of this particular challenge. So this is just a generic slide on Total. Many people may not know Total. It's not necessarily a household brand in the United States. It's very, I think it's more known in Europe and in Africa, but here for anybody that hasn't heard about Total, we're about 100,000 employees present in about 130 countries. We are, depending on how you rank it, the 4th or 5th largest oil and gas company or energy company in the world. Our net income for last year was about $12 billion adjusted. And out of that $12 billion, $1 billion was going straight for research. Now, we don't do only research on carbon neutrality, but carbon neutrality is part of our research roadmap. So the idea is to take advantage of the know-how, of the experience of a company like Total, who can really scale solutions up to tackle this idea of reduction of atmospheric carbon concentrations. One of the latest advancements in this, and this is an announcement that Total did on their website in December, but it's a joint announcement between Equinor, the Norwegian oil and gas company, Shell, and Total, is a project called Northern Lights. And Northern Lights, it's an integrated project where CO2 is captured, collected, transported, and last injected to be permanently stored under the seabed in the North Sea. And Northern Lights is not going to be an enormous project. I think it's more of a demonstration project. But with a project like this one, we can expect to sequester about 1 megaton of CO2 per year. So remember what I was telling you, we need to have about 3,000 megatons per year of CO2. So we need about 3,000 Northern Light projects if we want to be in those numbers. Right now, we have about 30, 35 megatons sequestered. So there is definitely a need for an industry and industrial scale-up systems to make this work. All right, so this brings me to the technical part of the presentation today. When we are going to be dealing with CO2 sequestration in geological surfaces, we are going to reach the limits of existing numerical simulation capabilities. Why? So I'm going to describe 5 specific technical challenges. The first one, near the wells, when we inject CO2, we're going to have well integrity and well injectivity issues. Anytime we inject something really cold into the subsurface, CO2 is going to be really cold in comparison to the subsurface. There's going to be challenges to get those volumes out from the well, cement and casing into the formation. Then, when the CO2 is going to go into the rock formations, it's going to trigger local changes to saturations, more global changes to pressures, and even more global changes to stresses in the subsurface. So it's going to rotate or move the stress states of the underground formations. And this can lead to something really important here, fault activation, where you have unstable or at a critical state fault blocks that could potentially get activated by those pressures or by those stress changes. What we want to do, of course, here is to trap CO2. So we have to understand where the CO2 is going to flow inside our reservoir. Where is the CO2 going to flow and how it is going to be trapped? And I think there's 2 things here, stratigraphy and just juxtaposition. We want to create a situation where CO2 is completely and forever after trapped in the subsurface. So we need to really simulate a wide area, not just near the well, but wide area where the CO2 can migrate and be trapped. Number 4 here, the seal integrity. So here, I think the challenge is that we don't want to simulate only the reservoir where the CO2 is going to be injected where it's going to flow and potentially where it's going to be trapped, but we need to also simulate everything around it. When you have fault activation, when you have stress changes, these are going to impact not just the reservoir, but all the surrounding formations. So all of a sudden you find yourself modeling a much more extensive area of your domain, and you're going to have very specific boundary conditions around your reservoir for trapping. And number 5 here, if you push this even further, the boundary conditions can even include the surface of here, the Earth, but it could be the ocean floor as well, where you don't want to see any surface deformations, and even worse, you don't want to see any microseismic events being triggered by CO2 sequestration. So those problems here, as you can see, those 5 challenges really are pushing our numerical simulation tools to their known limits. So what are the limitations? Well, there are of 2 orders. We have limitations in the physics and in the scales. So the physics first, because we're simulating complex fluids, the behavior of the CO2, its reaction to the local in situ fluids, the brine, the potential remaining hydrocarbons, the various salts that are in the subsurface are going to really create complexities. We are going to see viscous fingers, we're going to see dissolution effects. Those thermodynamical effects have to be taken into account. Also, we need to take into account the long-term behavior where the CO2 is going to be trapped or mineralized, and this kind of broad thermodynamical behavior must be taken into account. Then we have to take into account geomechanics. As I told you, the major risk for CO2 storage is loss of containment. And if we have geomechanical tools in place to simulate how the rock is deforming elastically or plastically beyond reversible transformations, we have the means to assess the risks of CO2 loss of trapping. And all of that requires coupled physics. So we have fluid flow, we have geomechanics that have to be simulated together. We can't take one without the other. We can't just use a regular simulator for reservoir formations that does mass and energy transport. We can't use a regular simulator that does just geomechanics. We really have to couple them together. Now the scales. Well, a lot of those simulations are happening over very long spatial extents. We're talking here of aquifer-sized simulations, thousands of kilometer squares of formation. And they're also lasting much longer than traditional numerical simulations would. We're talking here of simulations over decades, centuries of CO2 migration. So we cannot afford to have a slow numerical simulator that will take small time steps and not be able to scale up to really century-long simulations. Fortunately for us, there are solutions. So the solutions really are twofold, or I'll say they're based on 2 things. First on the hardware, then on the software. So first the hardware. We're starting to see more and more powerful computers, and exascale computing is within reach. The next big exascale computer that is going to come on at Livermore, the name is El Capitan, has 2 exaflops of computing power. So we're starting to break over this 1 exaflop barrier, and we're going into exascale computing. Now, if we want to really leverage those computing systems, we can't just take an old code and refactor it for exascale computing. We have to redesign it completely, almost from scratch, going back to the data structure and to the motion of memory and management of inputs and outputs for HPC systems. So we need to do that. Otherwise, we are not going to have a scalable code. It's not going to be able to handle very large surface or very large volumes of numerical simulation for a very long time. And we also need portability, and this portability requirement is an important one, especially because the I'd say the picture of technology in the exascale domain is really volatile. You have a lot of new technologies coming on, and I think we're right now in a cycle where hardware moves almost twice as fast as software. So you want to make sure that whatever software you write or however you write it, you can port it to the next best architecture that is going to come online. Now, from a software development point of view, here, the idea is that you want to start with exascale computing in mind. So a complete multi-physics solution, start with this and incorporate all the design choices that you need to be able to scale up. So how does that work and how can we make it work? Well, this, first of all, let me take a detour here. It's not just Total, it's not just Stanford, it's not just Livermore who wants to achieve that. This is a vision that is really shared by the experts of CCUS, carbon capture, utilization, and storage. Here, this is a report that was emitted in 2017 with about 250 industry experts, and they insisted on this HPC component strongly. They said, well, we can't really do this without HPC effort. A refocused HPC effort for CCS, carbon capture and storage, should expand beyond traditional reservoir simulation. So this was in 2017. This is just about when we started this particular project together. And in 2019, they went even a step further. They said, well, we just don't want this to be powerful and to be multi-physics. We also want this to be open source so that it can be used as a reference, as an auditable, undisputable, non-commercial reference that can really lead to transparency, openness, and also foster collaboration between the different agents that are going to be playing in that space. So HPC efforts, open source efforts, this is really what we can do here, what we can offer here. So how are we going to do this? Well, we're not going to do this alone. The first thing that we did was to look for partners, and Lawrence Livermore National Lab was added to this mix as a partner because of their HPC research and development on these particular architectures. They had all the experience for that. They also had a very strong experience in geomechanics. So the vision was aligned, they had the right skill sets. Now, Stanford, same thing. The vision was aligned, the skill sets were there. What does Stanford bring? Well, reservoir simulation is something that Stanford has done since the end of the 70s. And in the early 2000s, they completely revamped their paradigms for reservoir simulation with the creation of a general purpose research simulator that really helped Stanford develop world-class knowledge in numerical methods specifically for reservoir simulation. The couplings, the different discretization and gridding techniques that are needed for efficient reservoir simulations. This is really something that Stanford University, the Energy Resources Engineering, has a world-class, undisputed expertise. Here you can see in the red the logo of the University of Padova in Italy. We also work with them because they also contribute to this particular expertise in very specific areas of reservoir simulation, in particular contact mechanics. So they were rolled into this project as well through Stanford. And then Total, what do we bring? Well, the idea to have an industry partner here is to provide use cases, to provide the kind of industrial data sets and industrial operational constraints for such challenging simulation efforts. The other thing that Total brings is an understanding for how scientific computing looks in a production environment. We have a specific set of constraints that are different from those that are specific to purely research environments. We need a certain level of stability, of usability that we want to bring to the table. And so that, all of that, I'll consider that this is client needs, so to say. We are clients in the way that we work with other internal parts of Total, and they have their workflows and their understanding for how they want solutions to be accessed. And we have to bring this into this project. So this is the tool. It's called GEOSX. The reason why it's called like that is because of a previously existing tool called GEOS. GEOS was used for simulating geomechanical fracturing phenomena. X is for exascale. So now we have GEOSX, and the specifications of GEOSX. Here you see a beautiful picture. I mean, I find it beautiful because it wasn't an easy one to create. But here, this is an unstructured grid full of tetrahedra with faults that are represented explicitly. You see the faults are triangulated surfaces here. And we have injected 10 plumes of CO2. The mushroom-looking things that you see there are just CO2 concentrations near injectors that you have to imagine as vertical straws that would just push CO2 down the subsurface. And those simulations have been done using multiphysics approaches, whereby we have geomechanical deformations. This is where the faults really come into play. And elastic deformations of this particular reservoir. So, as said, we want this tool to be multiphysics, to have geomechanics as well as mass and heat transfer. We want it to be multi-level. I didn't talk much about that, but I think this is an important component of it. We can't really address the issue of scale if we don't have a multi-level simulation tool, something that can handle different levels of precision for different moments in the computation. So we're talking of algebraic multi-level. We're also talking of geometric multi-level, whereby we have different resolutions for different problems during the life of the simulation. Then it's designed for exascale, so that this program runs on your laptop as well as on the systems that the DOE uses, the exascale machines that are going to come in into play next year. It's strategic. Strategic means different things to different people. I remember the first time I heard somebody say this is strategic, it just meant that this is losing money. This is not the case here. I think the idea is that we are adopting and I think this is important, we're adopting a timeline and a risk profile that allows us to explore and that allows us to do things with a sense of long-term realization. We're not trying to find shortcuts to solutions. We're trying to find something that will be helpful to the community, not in 2022, not in 2030, but looking at 2050 as the timeline. And it's auditable, and this is part of this open source and completely open and transparent program. So everybody can take a look at the source code and ensure that anything that is in there is exactly what is being described, what is sold. There is nothing hidden. No magic happens behind the curtain. And I think this is very important if we want to ensure that CO2 injection is properly regulated, risk quantified. So this is the specific, this is broadly the specifications of the tool. Obviously, this is a very high level overview, but just to give you an idea for the magnitude of the effort, this is the 3 PIs, principal investigators of this project. So you can see Hamdi Chelepi here from Stanford. Hi, Hamdi, I know you're here on the call. I saw you before. Representing the reservoir simulation world expertise of the ERE department at Stanford. We have Joshua White for Lawrence Livermore National Lab, who is the subsurface transport group leader, and myself for Total. But on top of that, we have a whole team in Livermore, people at Total, people at Stanford, as well as people in Padova. Actually, this picture is even a bit outdated. Some people have come and gone. But overall, what I want you to know is that this is not a single person project. This is not even a small team, 5-6 people project. It's a 30 people effort. Some people are purely domain experts, reservoir engineers, geologists, geophysicists. Some people are purely IT experts. We have people that work on data structures, on portability across different systems, portability to CPUs and GPUs, for instance. And we have, I would say, a happy blend of the two. So various people bring in various expertises in this code. It's a C++ code, so relatively modular, and people can really tackle it with their best foot forward on their levels of expertise. So I'm not going to go through this slide because it's a busy slide and it's almost like looking at the catalog of what this code can do. It would be a little too much to go to it, but I'll just go with a bold letters here. So we have flow and porous media, we have solid mechanics, and the two being coupled together. We have advanced numerical schemes. We are using linear solvers, and in a very interesting way, we're trying to be agnostic to the linear solver packages as much as possible. So we're building against 3 linear solver packages: Trilinos, PETSI, Hyper. We have specialty simulation tools, I'll say, like embedded discrete fractures. We are using a relatively generic finite element interface as well as a finite volume interface. So the code to be multiphysics needs to have both finite element support as well as finite volume support. The tool uses relatively standard input and output formats. So we're not trying to stay locked into a specific proprietary format for our meshes, for our fluid models, for our geomechanical models. And this is sometimes a bit of a challenge because most companies that we work with are used to very specific proprietary formats. Here we're moving away from that. We're doing things in GEMSH for grids, for instance, or VTK for visualization. And the code is open source and has been released. And the important thing here is that we're still at version 0.2.0. So there is still a lot of room to grow in this code. It doesn't, I don't want to give the impression that everything is already finished and smooth and perfect. It's still an early code, but it already has CRS capabilities that can definitely be used for CO2 injection de-risking at this stage. So let's talk about what it does for research and what it does for operations. So far for research since 2019, we have published 19 journal publications based on GEOSX. There's 8 in preprints right now. Some of them are just using GEOSX as an engine to do other things. Some are dedicated to the deployment of GEOSX or the development of GEOSX itself. The last preprint I saw, I was actually quite excited about this one. I thought that this was an interesting paper that put all the things together. I'll just describe it to you in a second. Maybe it's going to trigger some appetite there. We work a lot on GEOSX itself. And a couple of weeks ago, we got a request from another group in Livermore that wanted to use GEOSX to do what everybody loves, machine learning, deep learning. So they did ESMDA, so Ensemble Smoother, with GEOSX as the source of truth. So they ran flow simulation for carbon sequestration. I think they did something like 80,000 cases. This thing ran on one of the Livermore clusters. I don't know how long it effectively took them, but it's something like 10,000 core hours, which was probably done in one night. And so they had 80,000 simulations of CO2 plume from an injector that they used as references, and then they could train a neural network against that and do monitoring and history matching of a CO2 plume using GEOSX results. So this means that really the tool is easily used even by people that are not part of the development team. I think that's perhaps important. And it can be parameterized and automated in a way that makes it possible to use it as the beating part of something like an expensive machine learning calibration exercise. But most of the publications other than that are really about GEOSX itself. The code is about 220,000 lines of C++. I think this is really just a very I'll say this is the most compact evaluation of the size of the code. If you unpack it and if you put everything else, the comments, the different documentation lines, the code is perhaps of the order of 500,000 lines already. And it's relatively active in the sense that people contribute to this code quite often. For 2020, we had about 1 code merge per day, so 1 new contribution to the code every day. And since it has been open to the community, it has been cloned many times, actually in a surprisingly high amount of times. Some clones here are done by the development team, so they shouldn't be counted. I don't have a means to discard them, but last time I looked, in the week of February 14 to 26, we had 1,700 clones of GEOSX, which I find very impressive. We start to have people that are not part of the development team come and ask questions and help us contribute to the code. People from Duke University, people from the INRIA in France. So slowly, it's becoming more than just a small team and a code that you need to be walked, by the hand into. It's something that can slowly be deployed. So to make precisely this deployment simpler, we have worked a bit on our DevOps. I know this is not necessarily super interesting, but it's the plumbing that makes everything work correctly. We use a cross-compilation build system. We rely a lot on third-party libraries, which means that we need a good maintenance system for those various third-party libraries. It's not always smooth because they change, they evolve, and we have to continue to stay compatible with them. But to do that, we use a continuous integration system where we have various HPC configurations that we target. Also some simple configurations like your classic Ubuntu or your classic Mac OS X configuration where we check that the code is not broken. And then we test everything. We have about 160 unit tests. We have about 190, I believe, integrated tests that we run, and we check for regression. We also run nightly benchmarks being smoke tests. I think some people call them, or performance tests, where we make sure that anything we do, we're not degrading performance, because that's in the end something that we probably are going to have to guarantee to the end users. And people, so Lawrence Livermore National Lab, Stanford, and Padova, and Total. And some recent partners have come into place. So we're open to more partnerships as long as people are aligned with the vision and are ready to contribute technically to the code. But the key message here is that it's a relatively open platform that we work on. In the interest of time, I'll skip this one a little bit. I'll just say that we are measuring performance, and we're achieving, for very simple operations here, near optimality on a specific GPU architecture. This was tested on Lassen. It's a GPU machine with Tesla V100s in Livermore. Of course, when we move away from optimality and from simple problems, our code is going to be less efficient, less performant. We know that, we expect that, but our idea is that when we think it should be performant and efficient, it is. An example of CO2 injection result, and this is, I don't know how impressive this is to you, but to us it was very impressive when we first saw that. Again, this is a CO2 injection simulation on a realistic data set. It has faults. The grid is completely unstructured. We use discretization scheme called mimetic methods. And the data comes here from a field in the Gulf of Mexico. And it was tested on parallel architectures with sense scalability. So we can run these types of cases. We can assert, for instance, the extent of a CO2 plume over a century of CO2 injection with this particular type of tool. Now, how can you contribute to GEOSX if you so wish? Well, you go to geosx.org. This is the website where we have our code repository. Here's where the source is located. And once you're in the source, you have everything you need to download it, compile it, and we have a documentation with tutorials and simple cases to get you started. Now, some key messages before I take any questions or before we discuss. Geological carbon storage is key to atmospheric carbon reduction. It's one of the important strategies to get to that. It's a challenge shared by scientists, businesses, and I didn't want to say politicians, but I just said all human institutions, I think, really should consider this to be an important challenge. There is a solution, and the solution space is in open source developments for multi-physics, multi-level, and HPC code. And we are really proud to work on this together, Total, Stanford, Lawrence Livermore, on this particular, in this particular solution space, to one possible tool to do that. And this concludes my presentation. I again want to acknowledge all the people that have contributed to GEOSX or to the research that fed into GEOSX with the support of Total, Lawrence Livermore, and Stanford University. Thank you very much.
Great, thank you so much, Herve. And why don't we open it up now for Q&A? If you want to unmute, you're welcome to, or you can type it into chat now.
I have a quick one. Oh, Margot, go ahead.
Oh, no, you can go too. That's fine. I was just going to ask you, Herve, I mean, the computational challenges and scientific challenges with these simulations are pretty interesting and wonderful, and you've done some amazing work in that area. The whole issue around carbon sequestration is, you know, there's a lot of debate around this, right? Whether that's really going to be part of the solution, how much it could be, and there are many barriers to that are really not just computational. And I was just thinking it would be kind of nice for people, particularly in CME, we have a lot of ERE people on the call who've heard about that before, to just say a bit more about this. What is stopping large-scale implementation of carbon sequestration projects apart from the technology? You know, what is really what's really driving that? It would be interesting to get that perspective.
I think I can tell you my perspective, but I'm happy to hear what others have to say. A lot of it has to do with finding the right regulatory space and finding the appropriate value chain. So many companies are reluctant to do it because they don't necessarily see this as an obvious value creation process. It is not true anymore. In more and more areas, there is value to be taken from CO2 sequestration, and not just by having the taxpayers subsidize this, but really by this becoming an industrial service, if you want, of CO2 removal, like you would expect any industrial waste removal service. And the Northern Light project, for instance, is based on the collection of CO2 from industrial agents around the North Sea, cement, steel, power generation, and they will not, this project will not exist without those emitters being responsible enough to dispose of their industrial emissions.
Gianluca, did you have a question?
Well,
I just want to say too that that I think I heard last week Al Gore say that we shouldn't treat the atmosphere as a sewer, and I think this is a very good way to just put it in blunt words.
Mm-hmm. Mm-hmm.
There are a lot of questions in the chat, but maybe just a quick one, and maybe I missed it. The time horizon for this simulation supposedly is very, very long, because you said you want to keep it forever. So how in terms of accuracy and in terms of sensitivity? Because obviously, as you increase the horizon, the expectation is that even small errors might pile up and create really, potentially dangerous situations.
Yeah, that you're right, and I'll even add to that it's not necessarily the same mechanisms that dominate the numerical simulation early on versus later on in the simulation, and we are even hitting some representation or some modeling boundaries there because. For instance, things like precipitation, mineralization, who are coming at the later stages of CO2 injection and plume stabilization are not yet in this code. We don't have any geochemistry per se in this code, but we're creating all the hooks and handles to include those later on. So I think we're not there yet. But we know that there is a problem there that we need to tackle.
Thank you. Karen, do you want to go through the chat, perhaps?
Yes, Herve, you have a
Yeah.
number of them now coming up in
Okay.
the chat. Mark says, how does your model address and incorporate uncertainty in model form as well as model parameters? And what more needs to be done to address that?
Yeah, excellent question. So uncertainty quantification is something that the oil and gas has been doing now for the good part of 20 years very actively. And in my experience of that, the parameter space has not ceased to grow. So we are incorporating more and more complex sources of uncertainties in our models. So things like, for instance, structural uncertainty, properties, operational uncertainties. And the key to addressing those, if you want, you're creating very large multi-dimensional spaces. And when your parameter space is so large, you are alone in the middle of your space pretty much every time. It's really hard to span and cover your multi-dimensional space. One key to help you do that is to have a fast-forward model. So this is where we get to having an efficient, numerically efficient simulation that can help you rapidly create those corner cases that can then be used to do anything you want. So you could do, for instance, reduced order modeling between the cases. You can do, like I described before, a machine learning or deep learning to interpolate between the cases you have created as boundary cases. So, but in any case, in large multi-dimensional spaces that you have when you do uncertainty quantification, a fast-forward model is the key, and I think that's what we're working on.
Great. Here's another question, Herve, kind of a follow-up to Margot's. Can you speak about the financial motivation besides tax breaks for private companies like Total to adopt carbon sequestering as a wide scale? And what do you see as the role of developing countries in this process?
So the Total has I'll say as an energy company, they almost have an obligation to go into this space, and at the moment they are not necessarily targeting a strong profitability in this space. They are okay having thin margins in this particular space because it is allowing and opening the path for many other technological advances. So I think there is an aspect of, I'll say it's a risk taken to show the capabilities, to show the capability of rolling out operations at that scale. It's not necessarily profitable right away, but there is a bet that it will be ultimately. Now, the second part of the question, can you remind me what it was, Karen?
The role of developing countries in this process.
Yeah. Okay, define developing countries. The interesting thing is that you find that developing countries a lot of times are actually ahead of the curve in many regards. They don't necessarily are going to go through the same steps as perhaps older, more developed countries, and they're factoring these types of considerations into their technological advances. So you see those types of projects in China, for instance, where it's built in their business model from the start. So they have a role to play, and they have, I think, they have the capabilities to really leapfrog over many older, more developed countries by having access to such technology.
Great. Now we have a few more technical questions here. One is, could you comment a bit more on the challenges related to the fluid modeling? Do you believe reservoir black oil simulations are able to handle such a complex fluid?
No, I believe black oil simulation is not sufficient for such complex simulations. The behavior of CO2, supercritical CO2, and its interactions with brine, the salted water, the salt water that is in place, is very different from the types of approximations you need to make for black oil simulation. In addition to that, you seldom have a system where you just have CO2 and brine. A lot of time you have other phases that are present, remaining hydrocarbons or salt in the brine. And you need a very specific description of your phase behavior if you want to be able to do that correctly, that black oil doesn't provide you with.
Thank you. Here's another one. What are the additional challenges that arise when chemical reactions need to be accounted for in the simulations?
Oh, okay. Well, this is this is a major bucket of worms right there. As you know, you have kinetics that you need to take into account, and right there we're at the boundaries of what we can do. A lot of time we assume instant equilibrium. We can't do that anymore when we have chemical reactions. This is probably the biggest challenge. Then after that, I think the reactions are relatively well known and measured, but their impact on the porous system is important. You may find that the properties of your rock, the porosity, the permeability of the rock, are going to be altered. How and at what rate, we are really just starting to gain knowledge in that. And actually the knowledge we have comes a lot from the shale gas studies we have, where we specifically study these types of behaviors. So we start to collect knowledge, but we don't have this modeled, and we're, I think, far from having it modeled in GEOSX.
Very interesting. Let's see another one here. Thanks for your great talk. How many cells are simulated in the last example of application? Is the thermal effect of injected CO2 considered for the simulation?
So the number of cells, I'll say in the industry right now, a good, a solid model, a solid simulation model is of the order of, 10 to the power 7 cells, 10 million cells. This is the kind of simulations that people consider to be large models. The largest model we've simulated with GEOSX was 500 million cells, and I don't want to say it went through it like butter, but it didn't fret at the size of the problem. Granted, it was a simplified problem in the sense that it was synthetic. It was not a real field. We don't have real field models that are that big, but we have been able to go as high as that. We could potentially go higher. We haven't tried. There was no numerical friction, so to say, when we went to 500 million cells with GEOSX. What was the second part of the question, Karen?
It says, is the thermal effect of injected CO2 considered for the simulation?
Not in the simulations I've shown. We have just started to incorporate thermal effects in GEOSX a few months ago. We haven't tested it, but it needs to be incorporated for sure.
Great. And here's one more, a bit broader. Thanks for the talk. Would you mind commenting on the performance of GEOSX in comparison with commercial simulators, such as the Eclipse?
It's okay. This is a tough one. We had a discussion like that this morning with Hamdi. Actually, it's not a tough one. It's an easy one. There is no commercial simulator that does that. Period. I don't. But let's dig into that question a little bit more. If we wanted to degrade the functionalities of GEOSX, in other words, we remove the multi-physics aspect and we just simulate pure flow simulation, we could do a comparison with perhaps intersect on unstructured grids. I think that would be useful in a way that it would perhaps establish the performance once and for all. I think we're working on that in the sense that we're trying to show cases where we can indisputably go above and beyond what can be done with those traditional commercial simulators. But
so
I don't have any results to show you.
Can I chime in with for 5 seconds?
Of
So
course.
Herve, I would stick with your first broader explanation. So there aren't existing commercial simulators where mechanics is an order 1 concern, and as a result it's going to be very hard to compare apples with non-apples. So I would stick with geochemical simulator.
But yeah, but it's a question we get all the time, so thanks for the question, but we'll dodge it.
Thank you. Thank you, Hamdi. One last one. I see we're just at the hour. I saw one slide on GPU. What is the status for GEOSX running on GPU? Ready both for geomechanics and fluid?
Yep. Yes. Just a simple answer, yes. Multi-GPU even.
Excellent. Excellent. Thank you again, Herve. This was fascinating. And I
My
look
pleasure.
forward to hearing more about all the upcoming publications and everything else you're doing. So congrats to your team so far. And thanks again for today.
Thank you very much.
Thank
Goodbye.
you.
Everyone,
Thank you.
have a good evening.
I'll stay on and we can wrap up together.
Absolutely. That sounds great. And we were planning to share this with everyone afterwards, the video.
Yeah.
So I think there were a few people who mentioned they wanted to catch it live, but they were busy. So I'm sure they'll appreciate it later on.
So did it work? Like, did the presentation work? Was there any glitches, any technical issues, or was it all?
I thought it was excellent. There were a few times where you faded or was, like underwater a few times, but it bounced back immediately. So it wasn't a problem.
Good.
And the slides were really clear, so we could follow along there. And I think it is very, very topical right now. And it was a large crowd. And people stayed on till the very end. So that's always a good sign. I was checking, there wasn't much drop off at all throughout the talk. So
Good.
No, thank you. It was very well done. And, of course, I'm sure there'd be a lot of students who would be excited to work with you and others at Stanford and Lawrence Livermore. So if you have any more open positions, internships or lines, always happy to share those with our students.
As a matter of fact, I think I sent that to Corinne.
Excellent.
We're pretty much, I'll say, open for students to work with us. The experience last year was a little degraded in the sense that we couldn't have them in person in an office. But I think we have since then learned a bit, and we're okay with remote collaborations, and we're starting to make it possible. I mean, unfortunately, they won't have the same cultural acclimatation as they would have if they were with us. And that I find is perhaps a bit a bit sad because they don't necessarily feel the same warmth after their internship to the company. But it is always possible to have interns, and I think we're interested in anybody that has skills in finite elements, meshing, anybody that has skills in even raw, hardcore, high performance computing implementations. We're looking for talents across the spectrum here. So
Great. Well, I'll touch base. I have a call with Corinne tomorrow, and we'll make sure that we get that message out loud and clear. There may also be an opportunity for students throughout the year to work on some capstone or other programs there. So to the extent that the data, or something they can work on, Carrie Hansen is the person leading that.
Yeah.
And I don't know if you've worked with Carrie, but I'm sure she'd be very open to some capstone programs working with your team next year.
Cool. Yeah. As said, I'm here. I'm really happy to collaborate with people at ICME, and I think this being relatively technical would be a good venue, and people can contribute at various levels of their expertise on this particular topic.
Oh, it's great. Well, thanks again. I better run and close it out. And thanks to all of you on the line.
Thanks everybody.
To the end. That's great.
Talk soon.
Bye, everyone.
Goodbye.
Take care.